तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, we have been discussing the merits of bipolar junction transistor, and we were in the process of taking a look at the heterojunction bipolar transistor. Just to see what we discussed, summary of what we discussed last time, the bipolar transistor, several merits. One is it has got high transconductance, which actually is exponentially dependent on the VBE. So, delta IC by delta VBE is IC by VT. For a given area, you get better transconductance compared to MOSFET and other things. Okay. Now, the threshold voltage is determined completely or solely by the band gap of the semiconductor. For example, if you take silicon, the cut-in voltage is about 0.65 to 0.7 volts. People take it about 0.65. If you take gallium arsenide, close to 1 volt cut-in voltage. That you can call as the threshold voltage, because its actually definition is actually the voltage at which current will begin to flow, at least 10% of the operating current that you want to do. Then we also discussed that submicron base widths can be realized independent of lithography. Okay. We have that advantage because you do not need to use lithography to control the base width. It is decided by a base diffusion and the emitter diffusion, if you are talking about diffusion, or it is decided by the epitaxial layer thickness or by implantation doses. So, that way it is controllable. You do not need to have electron beam lithography to get 0.1 micron technology base width. Okay. Now, that is about the BJT. Now, if with all these advantages, what modification do we need to get to that performance? One of the things that you need to do with BJT is to increase the cutoff frequency FT, you have to keep on reducing the base width. Okay, WB, the base width should be reduced, because after all the transit time decides the cutoff frequency based transit time. Transit time is WB squared by 2dn for NPN transistor, centimeter square divided by centimeter square per second. So, smaller the WB, smaller is the transit time, better is the cutoff frequency. Okay. So, that is what we are saying here. Now, when you reduce the base width, there are a couple of things happening. One of them is, if it is a doping is not too high, moderate doping, one of the things that happens, I can just draw the diagram here. Keep on reducing base width, you become more and more ambitious, say 0.1, less than 0.1, like that. If you go, what happens is, I have not written in the slide there, but you can see n plus p, n minus and n plus. You will have problem. This is one dimensional picture, but even in the one dimensional picture, one of the problems that you will have will be the depletion layer moves more into this region, but it also moves into this region. How much it moves into this region depends upon doping. If the doping is, even if it is about 10 to the power 16, then also this width can be about 0.3 microns very comfortably, very easily. So, if this width is 0.1 micron, there is a chance that the depletion layer will punch through. The collector base depletion layer will punch through and reach the emitter base junction when you talk of the base widths of 0.1 micron of that order. The only way you can beat that is increase the doping here, make this doping higher. So, punch through, collector to emitter punch through voltage calls for higher doping in the base region when the base width is reduced. Okay. That is one thing which I did not note in the slide, but that is a very important thing which one can see. So, punch through, emitter, punch through. Implying the depletion layer punch through, depletion layer reaching the emitter base junction, okay, limits WB, the lower limit on WB, unless NA is increased. In other words, what we are telling is you must increase NA if you have to go to lower at WB to avoid this problem of depletion layer punch through. Okay. You may say I will have a non-uniformly doped substrate, but how much is the punch through voltage depends upon the total doping concentration here. See, after all, if you reduce the base width, unless you increase the doping concentration, then the integrated doping concentration will not be sufficient, okay, because after all, when you have plus charges here on depletion layer, it calls for minus charges. The minus charges are limited by how many dopants are present here. Okay. So, when you reduce the base width, number of dopants present are less, unless you increase the doping concentration. You may like to go to 10 to the power 17, 10 to the power 18, that level, when you go to that level of 0.1 micron, but then you will have lot of problems associated with that. Let us see. So, this is following the usual scaling laws. Whenever you scale down, the dimensional doping must be increased, MOSFET everywhere. What other parameters are there? The other parameter that gets affected is the second one, is the base spreading resistance. Usually given by the symbol RBB dash. Just to note that B dash is some intrinsic point. So, it is RB, base resistance, which is coming there, which is external to the device, which is result of, I have it N plus here, okay, N plus layer there I have, and then I have this P region, P layer coming up here, okay. I have contact here for the base. I am showing the general structure that is in bipolar transistor. Instead of showing it vertically, I am showing it, put it like that. Usually, you will have top to the bottom, and this is the end collector. Okay. It goes up substrate. Now, here the current flow is like this, laterally from the base there is current flow, which actually supplies the recombination current and also which supplies the whole current to the emitter. The base current is lateral, okay. That is the one which is seeing this resistance, lateral resistance looking down is seen there. So, the resistance of that region depends upon what is the sheet resistance of this layer, okay. It is proportional to the sheet resistance of the layer, and the sheet resistance of that layer would be dependent upon how much is the thickness there, or to put it in simple terms, the resistance in this direction is more if the width is smaller, RBB. So, what we are trying to tell is RBB dash, okay, increases, let me just not put that, RBB dash from this portion and also all through, it is a spreading resistance. As the current flows here, something spreads out to the base contact, that is why we call it a spreading resistance. It is not a bulk resistance of this portion, its entire region is contributing to the lateral flow, because after all the current flow to the base is not just one point, it is all going like that. That is why we call it as a spreading resistance. So, that becomes more if the resistance, the area is smaller. Okay. And the spreading resistance is proportional to, can I remove this now? So, this is noted down now. The resistance actually RBB dash will be proportional to the RS, where RS is the sheet resistance. RS is the sheet resistance. Just put it down here. Sheet resistance is actually, RS is actually equal to rho divided by thickness. Okay. In this case, this is rho divided by WB, thickness. Sheet resistance looking from here is actually, when you put a layer, sheet resistance is what is the resistivity divided by thickness, okay, and thickness is WB, base width in this case. So, what is rho? 1 by Q N A into mu p, that is sigma into WB. Now, you can see if I reduce the base width, RS goes up linearly. If RS goes up, RBB dash goes up. So, why I put this particular expression is, what matters is the product of NA and WB. So, you can also put it in general as integral Q N A function of x, it may be non-uniformly doped, into WB into mu p for a p type layer into d of x, integrated 0 to WB. This is WB. Okay. That is the base width which I have put there, and over the entire base width, if you take NA of x into d of x product, integrate it, that is actually equal to NA into WB. So, what you are telling is your sheet resistance depends upon the total integrated doping. I can pull out the mobility and Q term, and what your left inside will be this, approximately I can put it as 1 divided by Q times mu p. Actually, mu p also will be dependent on mobile doping when you go to high doping concentrations. I am pulling it out just to show you. So, this will be equal to N A times d of x. What is that? 0 to WB. This is nothing but total integrated doping. That is what I was telling. Ultimately, what matters is how much is the doping concentration in the base, total number per centimeter square, okay, either in terms of resistance that you are talking of, sheet resistance, or in terms of punch through voltage also. It is not enough if you just increase the doping, it is actually total doping you must increase. Okay. What happens if you, now both the things point out to the same thing, that is whether you talk of punch through voltage, limitation to avoid, or reduce or do not allow this resistance to increase, both of them point out to that you require to increase the doping in the base region. Okay. If you reduce the base width, you better increase the doping if it is uniformly doped. If it is non-uniformly doped, of course, integrated doping, total doping. Now, there is some equation I put it here, just which actually is a well known equation, which comes up from the equivalent circuit. That is, this RBB dash, what parameter does it affect? That I have put it here. That is the maximum frequency, operation frequency, at which power gain is unity. In fact, if you make an oscillator, maximum power gain that you can get will be unity when you go to that frequency. In fact, from the equivalent circuit, it is everywhere you see this equation put. Okay. So, from the equivalent circuit, it is shown that it is related to cutoff frequency. You can improve the cutoff frequency by reducing the base width. So, that you can improve, but maximum operation frequency where power gain is unity is limited by Ft and also CJC, collector junction capacitance. You can reduce it, and if I have n minus layer on the collector, automatically depletion layer width becomes longer and the CJC becomes smaller. RBB dash. So, RC combination between the collector base capacitance and the base spreading resistance together bring down the maximum operating frequency. Okay. So, this is a general formula, I just borrowed it straight away, there is no point in spending time on deriving from the equivalent circuit. So, it hits the frequency of operation finally. So, you need to keep this RBB dash low, you can't allow it to increase. What you have gained by reducing the base width in terms of transit time, you would have lost in terms of maximum operation frequency because of increase in RBB dash. Okay. So, that is why from the point of view of punch through voltage and also from the point of view of base spreading resistance, maximum frequency of operation, you need to increase the doping in the base, integrated doping in the base. So, this is summing up what we have said now. RBB dash is the base spreading resistance and is proportional to the sheet resistance, which varies inversely as total integrated doping concentration in the base region. RS varies as inversely as the total integrated doping concentration in the base region. That is what we have said there in the statement. You must actually increase this quantity to reduce it and finally reduce RBB dash. NA, or rather total integrated doping NAD of x, should be increased when WB is reduced, so that RBB dash does not increase. Keep it within the limit. It leads to, what does it lead to? When you do this doping increase in the base region, what are the parameters which are getting affected? Okay, let us just take a look at that. So, when you increase the doping in the base region, several things can happen. One of them is doping Na is increased one is emitter base junction capacitance, transition capacitance. Okay. CTE, I have not expanded that there. So, CTE increases. Why? Just put it here. N plus already have 10 to the power 20, and I make this base width very small and increase this B. So, this, let me put it this way, let me put this as, to differentiate, N plus 10 to the power 20, this I will put it as P plus 10 to the power 18, I take it up with my anxiety to reduce the base width and also to reduce the RBB dash and prevent punch through, I make it P plus 10 to the power 17, 10 to the power 18 all through. Okay. Then what happens? The depletion layer width actually here is very small. So, result of increase in doping in the base reduces the depletion layer width, which actually increases the capacitance. That is this. And the moment you increase the capacitance, it is going to affect you through a charging time required for charging this capacitor. So, you would have reduced the base transit time, but you have increased the time required to charge this capacitor. So, you can talk of that as a transit time through this charging time required. So, your cutoff frequency will come down because this will go up. See, base width is reduced to reduce the transit time in the base, but you have to follow it up with the increase in the base doping, which actually increases the capacitance CT, which will increase, which will introduce delay in charging this voltage. Unless you charge this voltage, you charge this capacitor, there is no transport taking place. So, you have delays introduced in them charging the emitter base capacitor. This is one effect. What other effects will be there? This is one of the major effects. Other effect is if you go too much into this doping increase here, both of them, the width becomes small. That is why you go 10 to the 19, the upper limit comes up because of that. You go to 10 to the 19, the CT becomes worst, 1. Even if you do not care about CT, there is one more parameter which comes up. The depletion layer becomes so narrow that there will be tunneling current. Once you have tunneling current, junction behaves entirely differently the way you want. It can behave like, if you take a tunnel junction, it behaves like ohmic contact initially. In fact, it behaves like almost like ohmic contact there. You will have negative resistance characteristics, etc., but that is ultimate. Okay. So, these are two effects plus what happens to beta of the transistor. Beta of the transistor, what happens? So, second one is tunneling, chances increase. When I say tunneling chances, I am saying tunneling the electrons here, okay, that increases. Now, that is when you go to doping 10 over 18 and above, because you have to go to depletion widths which are something like 30-40 angstroms, otherwise it does not. Now, the transistor beta, the third one is the beta of the transistor due to fall in emitter efficiency. Okay, due to fall in emitter efficiency. If you do not recall, I will just write down some of the equations related to that. Okay. And the base width is so small, 0.1 0.2 microns, you may not have to worry about the recombination in the base. You may not have to worry about transport from the emitter to the collector. Transit times are very small compared to the lifetime. So, you will not have, you will hardly have any recombination. Okay. So, the current gain of all the transistors today, modern transistors, are limited by emitter efficiency rather than the base transport factor. In the olden days, alloy junction transistors where base widths were 25 microns, the beta was 40-50, controlled totally by the base transport factor. You do not have to worry about that thing. So, beta will be actually equal to current collected here divided by whole current injected there. Okay. So, what is beta now? IC divided by IB. I am neglecting, of course, the reverse saturation current there, DC beta if I talk. I think I will just have to go one step further down here. IC is equal to INC, electron component of current reaching the collector, standard symbol. Okay. You take the base region 0 to WB. Okay. Uniformly doped base region, let us consider that for simplicity, is actually NP0, electron concentration at x equal to 0 and this is 0. So, IC therefore is equal to area Q D N B into N P 0 divided by W B. Okay. N P 0 is actually N P thermal equilibrium e to the power of V B by V T. So, you have got I C therefore is equal to area into Q D N B into N P bar e to the power of V B E by V T divided by W B. Okay? That is the value. Now, this actually is equal to, this is a standard equation, I am rewriting it, emit area Q D N B into N I squared divided by N A in the base region. N P bar is N I squared divided by N A, thermal equilibrium value, okay, into e to the power of V B by V T. And this I can write also as area A into Q D N B N I square divided by integral N A into d of x. This quantity is a total integrated doping. In fact, if you write for general case also, you will derive that equation. Total integrated doping. Let's write it once more here with space. Area into Q D N B N I square divided by N A into d of x 0 to W B e to the power of V B by V T. Okay, this just to remind you, we all know it. I just reproduced whatever we have been discussing earlier in many of the lectures. You must have heard about these things. That is that. This is a total integrated doping. I can call it by NATB, NA total in the base, the denominator. Okay, now, please note at this point, the entire thing depends upon Ni square. If I make Ni square, if I have a device which has got the same integrated doping concentration, and if Ni is smaller, that current is smaller. Okay. If I take germanium device to use the same equations, this Ni will be much larger, I will have much more current. Okay. We will not jump into germanium device because of that, because the band gap is too low, it cannot go to higher temperatures. So, that is the thing. Now, that is IC. What is IB? So, let me just write down now, let me take up this whole portion, come back to this. Okay. So, IC is, I am rewriting area QDNB and I square divided by integral NAD of x 0 to WB. Similarly, this is INC, whole current injected from the emitter to the collector. Okay. So, similarly, IPE, whole current injected to the emitter. Okay. Injected to the emitter. Is IPE approximately equal to IB, because recombination current in the base is negligible. Otherwise, you have to add that also. Base current will be this whole current injected to the emitter plus recombination current in the base. I am neglecting that because base width is very small, nothing much recombined. So, IPE will be how much? Let me put this across to you by drawing a diagram here. N plus P N minus collector, base, emitter. That is the carrier distribution here, NP0, and everything was related to NP0 divided by WB. And here I will take this width WE small I think that may not be visible properly for you there, WE, and this is WB. So, this current component we have written now. All that we did was NP0 divided by WB into QDN into area, and NP0 is related to e to the power of VB by VT. Here, if this width WE is very small compared to diffusion length, how will that be? See, this is linear because base width is small compared to the diffusion length, and this width is small. Today's transistor, that width will be very small. So, that will be like this. So, this will be actually Pn0, this quantity. So, this will be actually equal to area QDPE. We are getting there, we are getting closer to HBT now. Okay, QDPE Pn0. I am just putting 0 to indicate that it is at the edge of the depletion layer, divided by WE, because that is a diffusion current uniformly doped. Pn0 divided by WE, that gives me dP by dfx. dP is this one in the emitter, dP by dfx is the slope Pn0 by WE. Okay. So, this I can write it as Pn0 is Pn bar e to the power of Vb by Vt. Pn bar is actually Ni square divided by Nd. So, this will be area. I will skip steps and put it as dPe Ni square divided by W Nd into We into okay. You got the IP, which is actually the base current, area QDP Ni squared by Nd. Ni squared by Nd is actually Pn0, thermal equilibrium. This is Pn bar e to the power of Vb by Vt. Vb by Vt I put here. Pn bar is nothing but Ni squared by Nd. Ni squared by N doping. Okay. Pn product equal to Ni squared. Thermal equilibrium Pn bar is Ni squared by Nn bar. Nn bar is nothing but Nd. So, what is this quantity? It is similar to that. So, now what I will do is this can be written as okay. So, since this is already there, I will remove from here, go back into this. So, IPE, let me write it once again, these two equations. So, IB is approximately equal to IPE, which is actually equal to area QPE. See, I am using the symbol suffix E there again, because we have now different regions. You have the N type emitter, N type collector. So, I am just talking of whole diffusion coefficient in the emitter. So, that is I put E there into Ni squared divided by integral Nd into d of x, integrated over the emitter, 0 to W, I am just putting integrate over the emitter length. integrated over the entire emitter length. Okay. That is actually this quantity, total integrated doping concentration. Okay. So, IC is approximately equal to INC, which is equal to INE area into e to the power VBE by VT. Okay. E to the power VBE by VT. Now, similarly, I can write down. I could have skipped this, but I thought it is better. INC area QDNB Ni squared e to the power of Vp by Vt divided by integrated over the base n A into d of x. Okay. Beta now is ratio of these two. So, now I can remove all these things which we have been discussing here, okay, because finally, we have got down the general equations for the collector current and the base current. Beta is ratio of these two. Notice we have taken the Ni here and Ni here is the same thing. Okay. What I will do now is, I will just assume that they are not equal. Supposing they are not equal, what happens? That point onwards, I think I have some of the slides which are put there. Okay. We will go to the equation, provide a continuity from here. IB is actually area into QDPE. I will put it as Ni. This Ni refers to emitter, whole current injected to the emitter. So, we are talking about doping in the emitter. Okay. I will put it as Ni square, okay, divided by Nd total in the emitter, where Nd total in the emitter is this quantity, doping concentration total in the emitter. Okay. That is that quantity into e to the power of Vb by Vt. Notice I have rewritten that equation, whatever I have written earlier, replacing Ni by Nie square. I just want to distinguish between the base width, base doping, base region intrinsic concentration and emitter region concentration. If it different, what happens? IC area Q D and B, electron diffusion coefficient in the base, that, okay, into, if you go back to this quantity here, this current is a current flow in the base region. All the properties are related to the base. The whole current injected, all the properties are related to the emitter. That is why you call Nie there. This one will be Nib. Okay. So, that is Nib square divided by, what do you call it now? This is now acceptors in the base, total in the base region. Na acceptor, total acceptor concentration, just a way of putting the thing, if you are writing integral Na d of x every time, you put that total doping concentration integral, okay, into Eb by Vt. In fact, when you find the beta, you divide this by that, area goes off. So, beta, which is IC divided by IB, okay, this cancels out, and you have got now D and B, okay, Nib square, they are remaining, this cancels Vb, okay, and in the denominator you have got NATB, okay, you have got NATB. So, I just put this quantity divided by Q gets cancelled, dPe. I think what I will do is I will write one below the other one, dNB by dP, okay, and you have got NIB squared here divided by NIE squared. And you have got NATB and here NDTE. Okay. It is the same equation that you have been writing in your maybe in your first course or so, but the difference is I have added these two things. I put these two. See, if the band gap is the same, Ni will be same in the emitter and the base, that will go off, and beta will be decided by dNB by dP, total integrated doping in the emitter divided by total integrated doping in the base. Okay. In fact, that is what I have put it here. Now, let us go back to these equations. So, all this effort has been to explain this particular equation, and I have written dNB by dP, NDTE by NATB multiplied by this quantity. This ratio will be 1 if the band gap in the emitter and band gap in the base are same, and you will get a beta decided by this. Now, you can see the beta of this transistor, if these two are same, will be dependent upon total integrated doping in the emitter divided by total doping in the base. What we are telling now, what we have been arguing about just now is, I need to increase the total integrated doping in the base. Why? If I reduce the base width, I must increase the doping concentration, and the total integrated doping also will be going up because of that. To take care, to ensure that because after all we saw the punch through voltage and also the RBB depend upon total integrated doping. So, this actually will, this ratio, if I increase this concentration NATB, okay, the ratio will go down, the beta will go down. Just you can take an example of about 10 to the power 18 and 0.1 micron, and here 10 to the power 20 into 0.1 micron, then you get 100. But if you take it even beyond that point, the beta falls down. Not only that, mobility also falls down in the base. But now, what we want to do is the ability to increase this unlimited by this punch through, unlimited by this tunneling, etc. Only way I can do it is reduce the doping in the emitter. If I reduce the doping in the emitter, what happens? See, what we want to do is, I want to reduce the doping in the emitter. See, if I have a transistor structure like this, N, P, N minus, I am keeping this N plus plus, N plus plus, plus there. Now, this depletion layer will become narrow. I can increase the depletion layer width by reducing the doping here. I put this N. Now, you see the whole thing is reversed. Base is doped much more than the emitter. Total integrated doping in the emitter is lower than the total integrated doping in the base. I can have this depletion layer going up like this, wider depletion layer, CTE will go down if I am able to decrease the doping. But my worry will be, if I reduce the doping here, if the band gaps are same in the two regions, emitter efficiency will go down, you will get a very poor transistor. Okay. So, with this reduction in the doping here, you achieve everything that you want. You can increase this doping as much as you like, you can that way you can reduce this base spreading resistance, you can prevent the punch through, and you can reduce the doping here considerably, so that the transition capacitance is reduced. Okay. So, now this is the situation described by this equation now. So, your intention is to increase the doping in the base, total integrated doping in the base, and reduce the doping here. At the same time keep beta high. How can you keep the beta high? Take a look at this. The only way you can do that is use the materials which have different band gap. NIB and NI should be different. Okay. What way do you want it? NIB squared is some constant to e to the power of minus EGB by KT, proportion exponentially to EGB, band gap in the base, and this is e to the power of minus EGE by KT. So, what will you get here? These are of course some of the explanations that are given here, integrated doping, given the symbol that. Let us say this is wider band gap, emitter is wider band gap compared to the base. So, EGE is greater than EGB. So, I will call it as delta EG equal to EGE minus EGB. Okay. So, now what will happen now? So, beta is dNB by dPe NDT emitter divided by NAT base. I want to cut that down. E to the power of minus EGB by KT divided by e to the power of minus EGE by KT. That is what we have written in the previous page, which actually is dNB divided by dPe NDTE divided by these too many suffixes, bit looks clumsy, but it tells you doping total concentration in the emitter, acceptor total concentration in the base, donor concentration total in the emitter, acceptor concentration total in the base, e to the power of EGE minus EGB by KT. EG is greater than EGB. I am taking it up. Okay. This is actually equal to, what is this quantity? This is a quantity that you get the beta if the band gaps are same, EGB equal to EGE. That is the beta of the homojunction transistors. Now, let me just put it like this: dNB divided by dPe into NDT by e to the power of delta EG by KT. Now, if the band gap here is smaller than that, you are gone. This becomes negative. If emitter band gap is smaller than the base band gap, this will be negative quantity. Negative quantity and beta will be even poorer. If the band gap in the emitter is larger than this, you can see even if it is just 100 millivolts larger, 0.1 electron volts larger, then 100 divided by 25, e to the power of 4, this is a factor of e to the power of 4, that is about 50, 54. So, you get a big factor here multiplying to this, which gives you the ability, if you choose the band gap of the emitter larger than that of, see the numbers are here. If you take a look at the whatever I have written on the board there, this is the thing. What we are trying to tell is, if EGE is larger than the EGB, this is large number. If this is large number, I can keep the beta high even if I reduce NDE. Now, you can see I have chosen a number to illustrate what sort of beta you can get by taking delta EG equal to 0.3 electron volts. Make the emitter that of aluminum gallium arsenide, make the base that of gallium arsenide. Delta EG is actually, we can get 0.3 very easily. Okay. You can get 0.3 even with the aluminum content much lower. You do not have to go to 0.4 aluminum content, x equal to 0.4. Even much lower than that, if you take delta EG 0.3, you can get very easily a wider band gap compared to that. Then e to the power of delta EG by that is about 10 to the power of 5, 0.3. delta Ig, that is 300 millielectron volts divided by 25 millielectron volts e to the power of 12, that is about that. So, this number is 10 to the power of 5. Now, you can see what you have bought by using an emitter which is not of gallium arsenide, but which is of aluminum gallium arsenide and base of gallium arsenide. Okay. So, that is 10 to the power of 5. Now, I will choose Nd total 200 times smaller than that of Na in the base. I can choose 10 to the power 19 doping in the base. I can choose emitter doping 10 to the power 17. It looks very funny when you think of the homojunction transistor, but here it is a reality, 10 to the power 17 doping. Okay. Then you get a factor of 200. About that, I just took a number, it is 200. This is that one. These are some of the devices people have fabricated with that ratio. That is why I am just putting these numbers. That will be and dN by dP, dNb by dP, because the doping is very high, you will not get all that high mobility there. You will not get all that large value of dN, so about 2.5 taken. But you do not have to worry about that ratio now, because everything is covered up by this quantity. So, 2.5 here for this ratio, and for this ratio is 1 by 200, 2.5 there, the ratio of NDT by NAT 1 by 200, base doping is higher than the emitter into 10 to the power of 5, 2038. So, you get a beta which is about 2000 with a doping in the emitter 200 times smaller than doping in the base. All that is achieved because you have used you have made a transistor whose emitter is a wide band gap material compared to that of base. So, what you see here is the N-type region doping of the order of about 10 to the power 17 aluminum gallium arsenide. X you choose, you do not want to go too much of X, because then you will have problems with that aluminum content there, and you will have problem also making a good ohmic contact here. Okay. So, you choose 0.1, 0.2 X, you will get that high band gap difference between the emitter and the base. So, aluminum gallium arsenide emitter, this is actually the, you can call it as a generic HBT that has been used, first time HBT ever used, or first time heterostructures used are L-gas gas, because there is good lattice match. So, gallium arsenide 1.43 and this can be 1.73, then 0.3 you get. So, you get beta which is very high. Okay. This is the schematic diagram which I have shown. Now, you go and make a device, you just make a device like this with all these doping concentrations, will you get that 2000? Just before we leave today, I will just mention 1 or 2 sentences about that. Actual devices when they made in Bell Lab, way back about 15 years back, they made this device with those doping concentrations, etc. They found a couple of things. One, the beta is not 2000, beta is about 30, very bad beta, and make the area larger and larger, beta becomes larger and larger. Okay. Apparently, it is a 2-dimensional effect that comes into picture, and when you see that just these equations, you jump with joy saying I can get beta with emitter doping of low value, but unless you take care of something else which is happening, you will end up with a low beta, much poorer than homojunction. So, we will see what is the effect that playing role in the next lecture. Okay.